Hand someone a deck of shuffled playing cards and ask them to sort it. Watch what they do. They will pick up cards one at a time. Each new card they slide left into the spot where it belongs. That is insertion sort, the most natural sorting algorithm a human uses. In the next 7 minutes you will learn why insertion sort matters. It has a secret superpower that none of the other O of n squared sorts have. Here is the plan. The one idea: maintain a sorted prefix. 8 lines of Python. One example walked in full. The best case input that makes insertion sort beat quicksort. Why Python's real sorting algorithm uses it as an inner loop. Here is the whole idea in one sentence. Maintain a sorted prefix on the left. At every step, take the next unsorted element and insert it into its correct position in the prefix. The sorted prefix grows by 1 each pass. That is your invariant. The first I elements are always in order. When I reaches n, the whole list is sorted. Here is what is different from bubble or selection. Insertion sort does not just swap pairs. It shifts a whole chunk of the sorted prefix one step to the right, then drops the new element into the gap. One shift per position is cheaper than one swap per position because it is fewer writes. Picture inserting a card into a sorted hand. You do not swap it pairwise leftward. You move cards right to make room, then slot it in. Here is the secret superpower. What if the list is already nearly sorted? Each new element only needs to be compared to the last element of the sorted prefix. If it is already bigger, you are done for this pass. One comparison, 0 shifts. That is O of n total work across the whole sort. Linear time. Real data is often nearly sorted, log files, sensor data, already sorted then appended lists. Insertion sort is faster than quicksort on these inputs. Insertion sort in 8 lines of Python. Define a function that takes a list. Outer loop for I from 1 up to n. Store the current element in a variable called key. Inner loop walks j from I minus 1 leftward while j is at least 0 and r at j is greater than key. Shift r at j 1 position to the right. Decrement j. After the inner loop ends, place key at position j plus 1. Return the sorted list. Same list we used for bubble and selection. Pass 1. Key is 2 compared to 5. 2 is smaller. Shift 5 right. Insert 2 at position 0. List 2 5 8 1 4. Pass 2. Key is 8 compared to 5. 8 is bigger. No shift already in place. Pass 3. Key is 1. Shift 8 right then 5 then 2. Insert 1 at position 0. List 1 2 5 8 4. Pass 4. Key is 4. Shift 8 right then 5. Insert 4 at position 2. List 1 2 4 5 8. Done. 7 comparisons, 7 shifts. The same list took bubble sort 10 comparisons and 4 swaps. Here is the nuance that makes insertion sort interesting. Worst case, reverse sorted input. Each new element has to travel all the way left. O of n squared, same as bubble. Average case, random input, still O of n squared. Best case, already sorted input, O of n. Linear. That is why real libraries use insertion sort as the inner loop for small or nearly sorted chunks. Tim sort, intra sort. And most production sorts switch to insertion sort when the sublist is under about 64 elements. So when do you actually use insertion sort? Rarely as the top-level algorithm. But on small arrays, say under 64 elements, it beats quicksort because the constant factors are lower. It also has a unique property. It is an online algorithm. You can feed it elements one at a time, and the sorted prefix is always valid. Useful for streaming data, real-time scoring, leaderboard updates. And it is a clear teaching example of the invariant pattern that underlies every serious algorithm you will ever write. You now have 4 sorting algorithms in your head and can compare them on different axes. Runtime, number of swaps, number of writes, adaptability to sorted input, best and worst case. Next up, merge sort, the first algorithm that breaks the O of n squared barrier for real. Subscribe and I will see you there.